one final example of absolute as well as conditional convergence for an alternating series. We have this series, n equals 1 to infinity, minus 1 to the n times n divided by the square root of n to the 6 plus 10. First thing we need to do, let's just work on the alternating series, all right? And remember, to do that, what we're going to do is we're just going to define a sub k, and we're going to get rid of the alternating factor. So that's going to be k over the square root of k to the 6th plus 10. And what we want to do is we want to see if it's non-increasing for values of k. So let's let k equal 1. And again, we start with that, the lowest bound. And then k equal 2, k equal 3, and maybe k equal 4. All right, just to make sure. All right, remember that's part I of our alternating series test. And so if I substitute 1 back in, that's pretty easy. Okay, that's going to be 1 over the root of 11. All right, and if I go through and substitute that back into graphing calculator, so 1 to the so 1 divided by square root of 1 to the 6th plus 10. Oop. Let's try that again. All right, and that gives us 0.3015. All right, now I'm just going to go ahead and take this and I'm going to copy it and substitute 2 back in and substitute 3 and substitute 4 where 1 was. All right, so that one looks good. And because it's smaller than the next, and we substitute 3, so that one's smaller. And if we substitute 4 back in, all right. So it looks like that our values are indeed non-increasing, or in this case, decreasing. All right, so I'm just going to go ahead and fill these in. So we had 0.302. All right, and for k equals 2, that was 0.232. And for k equals 3, that was 0.110. And for k equals 4, that seemed like it was approximately 0.062. All right, so it seems that we are non-increasing. All right, at least it looks like it, okay? We can't find any evidence to suggest that it's not. So next thing we're going to do is we are going to take the limit, all right? So the lim as k approaches infinity of k over the square root of k to the 6th plus 10. Now, to be able to evaluate this, we're going to take the smallest power or the highest power in the denominator and divide everything by it, which in this case is going to be the square root of k to the 6th, or k cubed. All right, so that's the trick that we need to do when we have this radical in the denominator. If it was the third root, we would take the third root of k to the 6th, which would be k squared. So now we get the limit as k approaches infinity of k over k to the 3rd divided by the square root of k to the 6th plus 10 divide k cubed, which is going to be the same thing as the limit as k approaches infinity. And we're just going to move the k underneath the radical and get back to k to the 6th. All right. In the numerator, this becomes 1 over k squared. And then we get the square root, and we make that a little bit bigger so I can fit everything underneath. Right. So this is going to be square root of k to the 6th plus 10 divided by k to the 6th. Now we can split it up into 2 monomial terms. So now we have lim as k approaches infinity of 1 over k squared divided by the square root of 1 plus 10 over k to the 6th. Okay, so all I did was just split those two into 2 separate small fractions. And now if we apply the limit, we know that that's going to go to 0, the numerator. And the second term under the radical is going to go to 0. Okay, so we end up with 0 over the square root of 1 plus 0, which is going to be 0 over 1, which is 0. Okay, so by the first 2 cases, we know that the alternating series converges. Okay, so we would say by I and I, we know that the series n equals 1 to infinity of -1 to the n times n over the square root of n to the 6 plus 10 converges. All right. Now, the question is, what does it converge absolutely, or does it converge conditionally? Okay, um, so again, what we're going to do is we're just going to take the absolute value and determine if the absolute value of the series converges. Okay, so if I was to take, so this would be n equals 1 to infinity of -1 to the n square root of n to the 6 plus 10, and I'm going to take the absolute value of that. Well, that's just going to turn into the series n equals 1 to infinity of n over the square root of n to the 6 plus 10. All right. Now, to determine convergence or divergence of this series, we can't use an integral test, all right, just because we know that if u is n to the 6 plus 10, that's going to give us 6n to the 5th as the derivative. This one looks like a prime candidate for us to be able to use a comparison test. All right, so I'm going to compare it to series n equals 1 to infinity of n over the square root of n to the 6th. All right, so remember with the comparison test, excuse me, you just look at the dominant terms, and the 10 really as n approaches infinity is negligible. And this is going to be equal to, if we take the square root of n to the 6, we know that that's going to be n cubed. So we get series n equals 1 to infinity of n over n cubed, which is going to be the same as series n equals 1 to infinity of 1 over n squared. Now, you probably remember that this is going to be our b sub n, okay? And this is our a sub n, okay, with our comparison test, okay? And there's two conditions, okay? One of which is we have to determine, is b sub n greater than or equal to all the terms in a sub n, okay? And excuse me, that b sub n and a sub n, those are the sequences, all right? So that's going to be these two, not the series themselves, all right? If that's the case, and the second condition is that series b sub n converges, okay? So if the terms of b sub n are bigger and b sub n converges, then a sub n converges, all right? So let's just go ahead and plug in the values for both, okay? So you probably remember we did this. So remember b sub n is equal to 1 over n squared, and a sub n is equal to our n over the square root of n to the 6 plus 10, all right? And let's let n be, let's say 1, 2, 3, and 4. Well, here's some good news. If we go back up, we just did it for this, right? So we could just copy these values back in for b sub n because we just approximated them for the other. So this is 0.302, right? And then right here, that was 232. And this is 0.110. And then finally, we have 0.062. All right. Now, what we're going to do is we're just going to find 1 over n squared. So this is going to be 1 over 1 squared or 1. And clearly that's greater. This is going to be 1 over 4 squared, which is 0.25. So that's clearly greater. This is going to be 1/9, or not 1 over 4 squared, just 1 over 2 squared. Excuse me for this one. So this is 1 over 2 squared. This is 1 over 9. And 1/9 is approximately 0.111. So it's just slightly greater. And then finally, we get 1/16 for the next one. And 1/16, don't know that one off the top of my head. I probably should. All right, that's 0.0625. This is 0.0625. Just looking back really quickly, this is 0.0624, all right, for the one term. So just barely, but it still is greater. And that's what's going to happen, is that as n goes towards infinity, they're going to start modeling the same behavior. But at least for small values of n, it looks like that it's going to be that b sub n is greater than a sub n. All right, so condition one's good. Now condition two, we have the series n equals 1 to infinity of 1 over n squared. And we want to determine what's the convergence or divergence of this series. And we know that this converges by our p-series test. We could use an integral test if we wanted to, okay? So this converges by p-series with p equal 2, which is greater than 1. All right, so what this means is two things. First of all, it means that this series converges. Okay, so by I and I, we know that the series n equals 1 to infinity of n over the square root of n to the 6 plus 10 converges. And finally, what that means is that we go back up to what it means to be conditional or absolutely convergent. Excuse me. And if we look at that, absolute convergence means that this converges. Okay, so that means that this time we have an absolute convergence. Okay, so hence, remember our original series a long time ago, n equals 1 to infinity minus 1 to the n over the square root of n to the 6 plus 10 absolutely converges. And that's what we were looking for, to determine. So the first step you want to do is you want to determine if the alternating series converges by itself, and then determine if it converges conditionally or absolutely. Okay, so that's it for this section. Again, when you're doing these sorts of problems where you have to determine for absolute convergence or conditional convergence, you're actually doing two tests. Okay, so you're doing the alternating series test, and then you're doing the test on series of absolute a sub n. All right, so so you're basically just doing another test. And let's kind of recall all the tests that we have so far. We're going to kind of add to our paper that we have. So remember, at the end of each section, you should have a sheet of paper, and you want to try to put all these tests on there. All right, so remember, we started off with the geometric series, and then we had the telescoping. Then we had the test for divergence. Then we had a p-series. Then we had an integral test. Then we had the two comparison tests. So just the general comparison test. And we had the limit comparison test. And then today, or not today, but in this video series, we took a look at the alternating series test. Okay, so now we have alternating series test. And within alternating series, remember, we have these problems where we can find conditional or absolute convergence. All right, so keep all of these in mind, because later in the course, we are going to need all of these series. Okay, in the next video, we have one more or two more series, or the next video series, no pun intended. We have two more tests of series, and then we can finally take a look at what we're going to use all those tests for.